Hey everyone, we've got a Codeforces Div 3 today, starting in a few seconds, and here we go. Alright, that's super easy. Alright, let's do it. Team compile. Cool. 489. Then I'm see like squares and cubes. Okay, got it. So we gotta omit 6th powers. Okay, so alright, and then we do while this is constant time. Didn't really have to do constant time. Month. That's right. Right to left. Oh, wow. How did I read that wrong? Oh, I see. Okay. A and S. Okay. Oh, okay. I think I get it. Oh, that's a little tricky because... No, it's not tricky. It's not tricky. Yeah. 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 And then d plus bd, if d plus bd is correct. If if d plus bd equals st, then we're good. B equals, or two string bd plus b, a running 10, s running 10. Also if d plus bd equals s mod 100, again, if s not equal to 0, and now okay. Oh, come on. I missed the minute. All right. Let's think about that then. Oh, we still have S. We're going to take A, we're going to take S. Remove leading zeros, and then, yeah, I think we're good. Oops, where did I do that? Did I submit? Okay. Okay, cool. Let's keep going. PIJ. Oh, okay. What? Doesn't someone not get one? Oh. Oh, I see. So. Oh, if you go to N shops, then you could just, yeah. Okay, so we're maximizing the min, so we should just binary search. And then if it's at least that much, what we're gonna do is, well, we need to pick n-1 rows that cover. Oh yeah, we just need any row with 2. Okay, that's what it is, right? M and then an O. That is kind of weird. My fingers keep trying to type the opposite order. All right. So we need some of that. I think we want this version, if possible mid. Yeah, we just want every column to be good. And we want full has pair. Yeah. So we just do this loop. Yeah, no count equals 0. Column j equal column j or pij. Has pair or row count at least 2. And every column has to be good. Three, 2, 4, 7. Oh, what am I doing? What am I doing? There could be way fewer shops then. No, why is 7 working on this one? It doesn't get the last column. Accumulate equals n. Oh, what am I doing? All right. All right, we're in the lead. Let's keep going. That's bad. Oh, okay. You need at least 1 less than 1, at least 2 less than 2, and at least I less than I. Okay, so you need to remove all of the I. We need to do a bunch of increments. Oh, we need to find, so we can do a greedy, we find the last thing that has a frequency of at least 2. Okay. Case template, and here we go. Let's close max. I like that better. Alright, and then like, okay, if and the answers x is -1. It's really more like this. Okay, set an answer. Okay, answers. We have to increment all these. Oh, what am I doing? Yeah, I should definitely do this minus 1 plus 1. Okay. We need to update move. If frequency nice. Equals 0, else if it's at least 2. Oh, this isn't even a set, it's just a vector. Okay, that's the extra case. If it's 0, then not extra dot empty, and frequency extra dot back is less than 2 extra. If extra dot empty then break. Everything is -1 at this point. Alright. So we're going to take extra dot back, extra dot pop back. Freak take minus, freak max plus plus, move plus max minus take. Is this what we want? I feel concerned that we can get a wrong answer on this. Here. Oh, don't pop back. Don't pop back. Oh, is that it? So at least max. Then it's move plus 1. Yep. Okay, that seems reasonable. Extra dot push back next, because that is nice. Alrighty. So F, G, and H. Yeah, let's go. This might be helpful to look at. I see. Oh, just find any. Okay. Don't you just rotate? Isn't that good enough? Seems like that's good enough. Okay. Key blocks of M lines. Okay, I think that's relatively easy. All right, so this is also a case problem. NMK. Okay, so there's gonna be K games where ceiling count is n mod m. Yeah. Anyway, yeah. It's a little silly. Offset equals offset plus ceiling count times smallest mod n. Okay, so Okay, so 2, 3, 1, 2, 3, 4, 5, 3, 4, 5, 1, 2, 3. Seems like it's good. All right, got a nice lead. Let's keep going. There's G and H. Could make sense to go to order. We'll see. Oh, that seems tricky. Wait, they also have a timer? Wait, what? Wait, so you have a bunch of cycles, permutation cycles. You do a swap, and then your other one is follow the cycle k times. Seems like either one is a reasonable choice. So they form connected components based on their k distance thing, because yeah. So 1, 2 is fine. So 2, 0, 1, 2. Okay, yeah. And then here, there's two components that can split at 1. Okay, so yeah, I understand. Okay, I know what to do for G. How are we going to not F. How are we going to find the neighbors? Okay, I got it. Okay, so xy type. And then we have two maps. And y to x. Not TII or something. Right. So we're finding all the neighbors. I guess I want lower bound. Alright, I'll just make these sets, because I don't want to do this. Less than 1 plus k. Then we're going to add an edge. I and it second. Yes. Okay. All right, now it's sorted and No. What is this? That's fine. All right, and one more problem. Still have a 14-minute lead, but that lead has shrunk. All right, let's go. Okay, so permutation. Swap changes the cycles. It either combines two cycles or breaks a cycle into two, right? If they're different cycles, they swap. And then it becomes a mega cycle. If they play the same cycle. Breaks into two cycles. So now you want to follow the cycle for case tips. Jump pointers idea, but that doesn't. That really messes up with the cycle swaps. So what can we do? We do something square root, right? How do you do a square root? It's like big cycles and small cycles. Actually not sure how to do this. Take some cycles and then The funny thing is the quadratic is probably pretty fast. You only need to speed it up a little bit. We can go for a while. If we don't see a cycle, then for a while, and if we don't see a cycle, then we know we're in. If we don't see a repeat, then we know we're in a big cycle. We know we're in a big cycle. What does it do? We know we're in a big cycle. We know we're in a big cycle. Oh, everyone knows where they go to after I got square root steps. Just a single jump point per thing. Oh, I think I got it. Oh, wow. $168, right? So 167 minus 106, that's how much do I have? 61. And this was a Oh no, this was a 2 hour 15, wasn't it? So I need to get it by... Okay, I have like 9 minutes. Okay, do it though. Do it. Okay. By void. Oh, oops, what am I doing? I can't do this. Okay, we got it. Okay, so again, 61. I just need to show it or submit it while it's showing 113. I cannot get it wrong though. Alright, I see. Reverse P, PI equals I. We can Alright, so oh, actually, it doesn't matter, does it? Just do this for fun. Alright, I think we're good. I'm just gonna submit. It's a lot of test pairs. There's runtime. Yep. Cool. Looks like we're good. Nice. Is that faster than other people? This is quite fast. I wonder if this is better than square root. All right, I'll be back to talk about the ideas in a little bit. All right, we're back. There's about 20 minutes left, and so far a decent number of people have solved all the problems, about 25. And yeah, it was interesting because SSRS and I had really close penalty, and then there's a big gap from us to everyone else. So lucky that lucky that I managed to beat him by a couple minutes, but it was also kind of planned based on the ICPC scoring. Yeah, it'll also be cool to see if Anand here, who's sitting on 7 problems, manages to finish problem H. Actually, that was kind of tricky. I had to sort of think from scratch how to solve it. But anyway, let's jump into the ideas. And I'll go through these quickly. There's a lot of them. So first, problem A. So this one's pretty simple. A string is a square if it's some string written twice in a row. You're given a string, determine if it's a square. Yeah, really simple. Just check that the size is even, and then check that the substring here is equal to the substring here. And if so, it's yes, otherwise no. You could also use the C++ string compare function. And I guess how would we implement this? It's like, I think we want to use this one if we do it. So, in fact, we could even get away with not checking this, because if n is odd, it will just fail the check. Let's try it using the compare function. We want 0 n over 2, and then we want the same string again, s, and we want n over 2. I think that's it. And then it returns int. We want to make sure this is 0 for equal. So let's just submit that. Cool. Yeah, so you can use substring, you can use compare, a lot of options, but pretty simple. All right, problem B, squares and cubes. Basically, you're given n up to 10 to the 9th. Count the number of integers from 1 to n that are a perfect square or a perfect cube, or both. I solved this problem in O of 1 time. That is not particularly necessary here, but basically, in fact, you can just do square root of n time. You can basically find the number of squares up to n, and then find the number of cubes that are not also squares. But I did an O of 1 time. Basically, I count the number of squares up to n by, you want to take the floor of the square root, and then you also want to add the floor of the cube root of n, and then you can use some inclusion and exclusion and subtract out the floor of the 6th root of n. And all these while loops are just making sure that I don't end up with a potentially inaccurate result from PAL. I guess the other thing I could do, yeah, I could use an epsilon here, and that would probably be, that might be better. I don't have to do any of these loops in that case. So, or actually this is potentially even easier. Just add half before we take the how. The reason for that is the only case where we'll have some precision issues are if it's exactly the number we want. And in that case, oh, it's upset that I'm, okay, there we go. Yeah, in that case, it's going to potentially the answer we want is 3, because we're taking the 6th root of 3 to the 6th, but instead we get back 2.99999. We convert that to an int and we get 2. So to avoid that case, we can just add half to n. And because we're not actually going all the way to n plus 1, there's no way we can end up bumping up to the next integer. So this is actually a lot better than what I did. Let's just submit that. Cool. Either way, it's O of 1, but you don't have to do O of 1. You can do O of square root of n, and that's totally fine. The only thing you can't do here is O of n. But yeah, a couple different ways to do it. All right, problem C. Okay, so problem C, they give you Tanya's janky addition algorithm. She takes 6 plus 5 and she gets 11. And then she just writes 11. And then she does 3 plus 6 and she gets 9 right here. And then she just keeps appending to the left and ends up getting way more digits than she should. But you're given A and S and you want to figure out if there's a B, such that using Tanya's algorithm, A plus B will get S. So this sounds tricky, but there's one thing that actually makes it pretty simple. If you think about the last digit of A and the last digit of S, there's only one last digit of B that will end up making that digit. This is because of, arithmetic modulo 10. So we're basically doing things mod 10 in this case. And then once we do that, there's only two cases. So we take the last digit of A, last digit of S, and we know that it's basically going to be SD minus D mod 10. We do an extra 10 so we don't end up with something negative. And then there's only two cases. Either D plus BD is already equals SD, in which case we're good. We just add this digit to the front of B and then remove the last digits of A and S. Or D plus BD is, instead of being 7, it's like 17, for example. And in that case, we need to make sure that the last two digits of S line up with that. If so, we put this digit in the front of B, we remove the last digit of A, and we remove the last two digits of S. And if neither of these cases applies, we already failed, so it's a -1. We do this while S is still not 0. And then at the end, we need A to be 0. Otherwise, A has extra digits and it's also -1. And then finally, this just removes the leading zeros from B. But it makes sure that it leaves at least one leading zero or one leading zero in the case that the number is 0, which is kind of a tricky one. Oh, I guess A is less than S, so that's not a problem. Okay, that would have been a pretty tricky case otherwise, but we did handle it here. So in theory, if this were allowed, 7, 7, it would print 0 instead of empty string. All right, problem D. So this one was tricky. There was quite a drop off in solve count from C to D. And basically, the statement's kind of long. I won't go into the entire statement, but the idea is we're maximizing a minimum. So whenever you hear that, you should think about binary search. And when we're doing binary search here, what ends up happening is our 2D array, or our matrix here, turns into a binary 2D array. So it's like, yes, this is good enough, or no, it's not good enough. And we need to pick n-1 up to n-1 rows where we get, for every column, there's at least some yes in that column. And the only tricky thing there is that we have n-1 rows. If we could pick n rows, all we need to do is we just need to check that there's a 1, or there's a yes in every column, because in that case, we'll just pick a row for every column and we'll end up picking at most n rows. But since we need to pick at most n-1, what that means is we need a row that satisfies at least 2 columns. And if we do have that, then we start with that one and then we just pick rows for the other columns and we'll end up with n-1 at most. So then we're good. So yeah, that's what we checked for. So this is the binary search on the answer. Checking for if a certain cutoff is possible. Just go through the 2D array, and there's two sorts of things we track. One is has pair. Has pair is true once any row count is at least 2, and then column is true once any element in that column is a yes. So we need both has pair and every column is yes. Oh, I guess I could have done this. Is it all of? Okay, so I guess I could just do this. All of, begin, column, and then this is going to be kind of silly. Pull x, return x. But it's the same. I ended up adding up all of the bools and making sure it was n, which is also fine. All of it is also fine. Either way is fine. All right, so that's D. Let's talk about E. Yeah, okay, so E is we're taking each number from 0 through n, and we want to know, can we make the max of the array equal to exactly this number by incrementing values in our array? That's the only thing we're allowed to do. And if so, what's the minimum number of times we need to do that? So the main idea here is, in order to get a certain max, you need to make everything equal to max, not equal to max, so you need to increment all of them once in particular. And then for everything less than that, you need to reach 0 through max minus 1 at least once each. And the condition we actually need for that is there's at least 1 0, there's at least 2 zeros or 1s, there's at least 3 zeros, 1s, or 2s, and so on. And that tells us yes or no. The only remaining thing is to figure out the minimum number of moves. For that, I keep a running list of which numbers have extras. For example, if there are 2 3s, I can take one of the 3s and increment them up to some number that I want, and I'll still have a 3. And then, yeah, it's just a greedy approach. We always want to use the biggest extra number we have to make our current number, because that will take the fewest number of steps. And it ends up being O of n time. You can kind of follow along the code here. Running frequency is the sum of frequencies so far. We need that to be big enough, because if it isn't, then we just can't solve it. Let's see. Yeah, and then if we don't have the current number, we need to look for something that has extra to bring it up. If there's nothing, we cannot make this number. So we actually break, and all of the maxes bigger than that will fail. Otherwise, yeah, we take that number, update some frequencies, and then add the amount that we have to move. So this code, it has a little bit of a tricky logic, but it ends up working out. It's O of n time, and yeah, that's the main idea. All right, let's keep moving. Problem F. Yeah, so basically this problem, we need to divide up people into tables to play games for different rounds, and we want to kind of make everything as even as possible. Each table either has n over m floored people or ceiling of n over m people. And we want to make sure the number of times a person played at a table with the extra ceiling people evens out as much as possible. So no player should have been at a bigger table 2 times more than another player. We want them to be as even as possible. They should be within 1 for everybody. This is actually, it turns out pretty simple. So let's say, for example, we have 10 people and we have 4 tables. So there's always going to be 2 big tables and 2 small tables, right? And the algorithm here is just, I'm going to call these 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we can think about it this way. The idea is just to start the big tables from where the big tables ended last time. And then keep going, and then you would also wrap around and then go here. And then the next time, big tables start here. Oh, I missed one. Yeah. And you can see here that we're never filling out these big tables unevenly. The next round always balances out the previous one as much as possible because it prioritizes the people who have had more small tables. And that's the entire idea of the solution. The code is actually a little bit longer because we have to make all these vectors and add all these numbers and then print all these vectors. But that's really the key idea. So it's actually pretty simple. All right, keep moving along. Problem G. So in problem G, we have a bunch of mines, and they explode in a plus shape. And you know K, which is how big the plus shape is. And each mine has a certain time that it will detonate. And so we want to explode everything. We can also explode 1 thing per second to speed it up, and we want to know how fast we can finish everything blowing up. And things that explode in a plus can end up exploding other mines, and then there's a chain reaction that occurs instantly. So the main idea here is this actually turns into a graph problem where one mine is connected to another mine if its explosion would reach the other one. And notice that the connections are bidirectional. So if mine A explodes mine B, then mine B will also explode mine A because they're symmetric in how they explode. So what we really end up with here is a bunch of different connected components. And within each component, the only thing that matters is the minimum time out of any mine that it has. This one. And once we have that, we just have a bunch of components. We can boil it down to just a bunch of components. Each component has a certain time, which it will automatically explode by that time. And then we can prioritize a few things to speed up. And then once we have that situation, it's actually just a simple greedy where you sort the component times and you speed up the, the j worst times, right? And you can try this for every j. So the only thing left is to find the components. The way we do that, we can check out the code, is we have a map for each x of all of the y's, and we have a map for each y of all the x's. And when I'm looking for a neighbor, I look at my x and I find the next biggest y, and vice versa for y to x. And that is, those are my only potential neighbors in the setup. It's actually, it's actually more than that, because if I can go up to KOA, I could reach multiple mines, but I'm only going to create edges along a single path. So, if mine 1 can reach mine 2 and mine 3, that's fine, because we'll just make an edge from 1 to 2, and then we'll make an edge from 2 to 3, and they'll be connected indirectly. So that's the main idea. Just take lower bound on the set of things with the same x, and check the k condition, and if so, add an edge. Same thing for y to x. After that, we just take the minimum component time for every component and sort those, and then do the greedy that we talked about, and that's our answer. All right, one last problem, problem H. So this problem it was a little bit tricky. The statement is pretty simple. You have a permutation. There are two operations you want to do: swap two elements of a permutation, or basically take I and assign I equals pi k times in a row, and then print what we would end up with. The main idea here is we have a permutation breaks down into cycles, and so we're kind of just following the edges along the cycle. And what's tricky is that cycles can be pretty big, and the swap operation will actually, right here, it will actually join two cycles or break up a single cycle into two. And you can go down a rabbit hole of thinking about how you're going to maintain these cycles. But in my case, that didn't actually lead to a solution. One thing we can notice is we have 10 to the 5th, and we have actually a lot of time, 4 seconds. So we can definitely squeeze in something that has, n square root n runtime. In this case, what we can do is basically we can pre-compute. Okay, well, we already know what happens if you follow x one time. It becomes px, right? Let's take the value square root of n, and let's pre-compute for every x what happens if you follow px square root of n times. That's the main idea here. So here, this is my square root constant. This is the best constant in terms of runtime. I tried out a couple of different ones here. Yeah. And this is the idea we're talking about. We jump x forward s times, and we compute that. So that's s jump. We pre-compute that for everybody. And then the query is pretty simple. While k is at least s, we can jump s ahead and then subtract s from k. And then afterward, we have a remainder that we just do one by one. So the real question is the swap. How do we handle the swap? Well, when we do a swap, there are only up to O of S things where the S jump is invalidated. And that would be X and everything behind it up to S steps, and Y everything behind it up to Y steps, or sorry, up to S steps. So we're actually going to just fix all those values by computing the S jump for X and Y, and then walking backwards. So we need to track the reverse permutation here. We walk backwards S times and then fix those S jump values. So yeah, that's the main idea. We have n squared n pre-computation here. This can be optimized to n if you really want to. And followed up by type 1 queries will be, this will just take S time, whereas the type 2 queries will take n divided by S plus S time. And that's why we choose S to be square root of n. All right, so that's the whole set. Contest is over. Okay, it looks like a decent number of people did finish the set. Anand had a couple TLEs. I wonder if maybe he was trying a quadratic or what he was doing. Let's see, we can check it out. Okay, we cannot check it out, I guess. Oh, it's still testing something. There is running. Forbidden? What is forbidden? Oh, Mike. This normally works. I'm not sure what the deal is here. I think it's finished. All right. Let's see what he submitted. Yeah, he just submitted the brute force. And he tried to do 2 steps ahead. It's interesting. All right. Anyway, I think that's going to be it for me for this video. Hope you enjoyed it. And feel free to subscribe to the channel if you want to check out some future videos from me. But otherwise, I'll see you in the next one.